Swayam Prabha. Digital India. Educated India.
Jnanam Paramam Dheyam. Knowledge is supreme.
So, the proposition is, and this is used many times, not only in commutative algebra, but every subject. It is like a machine. This. So, let 0 x dot y dot to z dot to 0. Let us write this as f and g be an exact sequence of complexes. Okay, then the sequence, which sequence? Now I will write down the sequence. So, Hn(x). What does this mean? This means when you look at this complex and then nth level, at nth place, this is homology. That means this is kernel by image. If for some reason, if you look at this n to be negative side, then one should write it here, but do not bother about it. It is only think at which position its kernel equal to the kernel by image. That is called the nth homology of this complex. Then Hn of y dot and then Hn of z, and there is a map here which is induced by this f. So, that is also denoted by Hn of f dot. We will define this Hn of f dot, and here Hn of g dot. This is right. Okay, this is so at the next level. That means if you change this position from n to n minus 1, then you have this also, no, Hn minus 1 x, Hn minus 1 y, and so on. And now, so this is Hn minus 1 f dot, this is Hn minus 1 g dot, and this side also there is. And now so we will define these maps and what is called a connecting homomorphism. So, these pieces are connected by the maps here, those are called delta n. This is called connecting homomorphisms. Okay, so what do you want to define? We want to define this Hn, this Hnf, Hng with delta n, so that this long exact sequence what we got is exact. That means that each stage there kernel is image, is exact sequence of A modules. And ultimately we will measure the homological dimension by how long is this sequence. So that is the measure, and then we will define what is the homological dimension of a module, and then we will characterize the regular local rings by looking at the supremum of the homological dimensions of the modules over that ring. So, right now our problem is to define Hnf, Hng, Hnf, that means similarly we will define this also, and the connecting homomorphism. Okay, so how are you going to define this? So, the best is to draw a diagram. So, obviously this is what? this is by definition it is at nth stage, that means xn is involved. So, this will be xn. So, the kernel will be inside xn and the image is also inside xn. So, this is some submodule of xn divided by some other submodule of xn, right. And however the where are the submodules are coming from? They are coming from the kernels of kernels and images of these fn's. Okay, so we have come down to this level. So, 0 go to nth stage means you have to read these given complexes at nth stage. So, we have, because the complexes sequence is exact, we have this xn, yn that is fn, and then zn that is gn, and this is 0. And remember, we want to define from homology at this stage means there is xn minus 1 here, xn minus 2, this is d, this is dn, this is dn minus 1. Oh, for some reason I have changed to the lower, does not matter, okay. This is yn minus 2, this is zn minus 1, and of course, this zn minus 2 here, this is exact here, this is exact here, this is exact here, this, and maybe here also I will write one term yn plus 1, and this is zn plus 1 to 0. This is dn, this is dn, dn minus 1, dn minus 1. Such a thing is there, such a thing is given to us. And what are we trying to define? We are trying to define a map from hn of x, this to hn of y dot. This is what we are trying to define. So, take any element here. How does any element look like? This is what, this is obviously the kernel by image. Kernel of whom? Oh, it is this stage, right. So, here kernel of dn mod kernel of dn plus 1, image of dn plus 1. So, this is kernel of dn divided by kernel of dn plus 1. By definition, this is by definition. Okay, so take any element here. Any element here is a class, residue class of some element in the kernel dn. So, therefore, then element I will denote by, say, what do I denote it by? Z bar, Z bar, not Z, X bar. And we want to define this map, right. So, what is the obvious choice? I just take this x, so that is, this is in here, no? This x is here. It is in the kernel of dn, in particular it is in xn. So, it goes 0 here because it is in the kernel of dn. So, obviously, what do we try? That is fn x, you apply fn to that and take the bar of that. But first you have to check that this fn is indeed in the kernel of this, and we will take the image then. So, this way it goes to 0. So, therefore, this way it will go to 0. This way it goes to 0 means this fn of x belongs to the kernel of dn. So, therefore, this makes sense. because this is by definition, this is the kernel of dn divided by image of dn minus 1 or dn plus 1. Dn is dny really, right. So, what we observe that this xn is, if it is in the kernel of this, then fn of that is in the kernel of this. So, therefore, it makes sense to talk about the residue class image of that kernel by dn. So, that is the map, and now we have to check that this is well defined. That means, if I change a different representative class, then they are same there, but that is, I leave it for you to check that this is well defined. So, similarly, we would have defined from here to hn z dot. So, this is the easy part, and check that it is exact, means you have to check that if somebody is the kernel of this equal to the image of this, but that will again follow from the fact that this each part is exact, each layer is exact. So, from that, so that you check that way, but the more little bit tricky is defining that connecting homomorphisms. So, connecting homomorphism means, now what do you want to define? We want to define from hn z dot to hn minus 1 x dot. This is what we want to define. That means what? That means, where is this hn of the z dot, that is somebody here, and from here you want to go down to here, right. So, we will have to change the diagram. So, what do we do? Okay, so you take an element in here, that means it is here, right. Here means it is in the kernel of this modular image of this. So, we have taken an element z here. And what are we looking for? We are looking for somebody here. We are looking for somebody here. Then it will be in hn minus 1 of x dot. So, this is kernel here. So, this is surjective. So, you choose somebody here which goes to there, then because it goes to 0 here, that one will go to 0 here, but then this one goes to 0 here, that means that image here is going to 0 here, that means that image here is coming from somebody here, and that is the required pre-image we look, right. See, z is coming from here, y, this y goes to 0 here. So, therefore, that is the image of y here, which is, let us call it y prime, that goes to 0 here, but this is exact. So, therefore, this y prime will come from here, and that is x prime. Now, you check that this x prime is in the kernel of this, but that, to check that, it's all, again you change it where what you want to do it, and then you take the image of that, and that is the required map. So, this one will be z bar going to that x prime bar, and we have to check several things here, that all these definitions, they do not depend on the pre-image of the, see, we are choosing x, we are taking the pre-image of x, but it may have many pre-images. Okay, having defined that, then we have to check that this resulting long sequence is exact, this resulting thing is exact. That is also again diagram chasing, because you want to prove at this stage kernel equal to image, and so that is also, then you take an element here, goes to kernel and prove that it is coming from here. So, that you have to chase that diagram, that is called diagram chasing. Okay, so that is complexes. Okay. Okay, now, and again, if you have also the functoriality. So, okay, so let us first first give some examples of functors. So, what is a functor? Functor is the analog of the function in set theory or map in set theory. So, that is set to set. Now, we do not have sets, we have a category. The category has objects and morphisms. So, C is one category and C prime is another category, and then we are looking for some associations. Now, this association should be compatible with the objects as well as morphisms. So, first of all, so this is usually denoted by script letters F for functor, and so each object here, suppose A is not A, V is one, think of this as modules category. So, I will denote the objects by V, W, etc. So, if V is one object here, it should associate object in this C prime. So, that is F of V. So, this is the association in such a way that whenever I have a morphism here, the corresponding thing, corresponding objects which are associated under F, so they will also have morphism between them. The question is whether direction is kept or direction is reversed, and both the things are possible. So, if the direction is kept, that is called covariant. We will see an example, and if the direction is reversed, it is contravariant. And in such a way, that if I have a composition, then we have the composition, whether you take a composition before and then apply F, or apply F and then take the composition, these results should be same. So, that is all this together is called, F is called a functor. So, now 3 examples we will see. So, examples, concrete examples. So, you take our category A modules and the category of sets, let us take. So, here the objects are sets and the morphisms are maps. Here the objects are modules, A modules, and the morphisms are A module homomorphisms. So, now I have a functor here, namely F, namely this is a forgetful functor. You take a module and forget that it has a module structure, think of it as a set only. So, this is associated to that, and then when you have a module homomorphism, you forget that it is a module homomorphism, it is a map also. So, that is, this is true from any category to the category of sets, where the objects were sets, Or you could have also done category of A modules to category of abelian groups. You forget the module structure, but keep the abelian group structure, right. So, that is it. Or another, so, and note that all these examples are under covariant, because the direction of the morphism is not changing. Whereas, now one example we have been seeing, though now category of rings, commutative rings, do not take arbitrary rings, commutative rings. So, this is a category. So, the morphisms are ring homomorphisms, and note that ring homomorphisms for us, the ring homomorphism means it should carry identity element to identity element, that is not automatic, and many books do not assume this, but we do assume ring under ring homomorphism 1 goes to 1. From here we have defined a functor from this category to the category of topological spaces, and this was spec. Any ring A mapped to spec of A. Remember, the spec of A is topological space with the Zariski topology, the prime ideal set of all prime ideals, and there we have put a topology on that, and with that topology this the spectrum is a topological space, and the closed sets where the V of A's, these are the closed sets. These V of A is by definition all those prime ideals P such that A is contained in P, and then we have seen that, or we have seen in other courses, that this collection forms, they satisfy properties of the closed sets in a topological space, and therefore, it is a topology. That topology is called as Zariski topology. Now, here we have also seen that if you have a ring homomorphism from A to B, then ring homomorphism, the map on the spectrum level is the other direction, because how do you define it? You take a prime ideal Q in B and then contract it, Q intersection A, this is the map. So, the direction changes, and we have not checked in our course, but you would have done, or maybe it is easier to check, that if this is a continuous map, this is continuous. In the if you take a Zariski topology here, Zariski topology there, then this is a continuous map. So, this way, and the gain is we are going to study these rings and sometimes compare it here, the spectrums. For example, if you want to prove two rings are isomorphic or not, if they are isomorphic, then the corresponding topological spaces will be homeomorphic. So, for some reason, if you have information that one ring has only one prime ideal and the other ring has two prime ideals or more, share only the cardinalities, then they cannot be homeomorphic, therefore, the rings cannot be isomorphic, like that. And also you might have studied another functor, which is also very useful, that is from the topological spaces to groups, category of groups. So, there is a nice functor called pi 1. So, in a topological space X, you attach a group called the first fundamental group pi 1, the first fundamental group. That is that is defined by using homotopy, etc., and then that is a group, but unfortunately it may not be abelian group and so on. So, that is usually one gets information. For example, if you want to prove some topological spaces are homeomorphic or not, this pi 1 is used, and not only pi 1, but there is a bunch of pi n's, there are lot of functors. And this study became more and more in the late 20th century, more and more common. Okay, so another important functor for us, there are two functors, and probably you would have studied their properties. Now, get back to our A is our fixed ring, fixed commutative ring, and we have the category of A modules. There is a functor from category of A modules to category of A modules. So, that means what? Given a module, I want to associate a new module. So, for example, I would have fixed a module, some fix W, fix A module. Then you can do it home A V W. So, this obviously, this W is fixed and this V is varying, right. So, this functor is denoted by home A dash W. Or why did you prefer one? So, you could have also done the other way. So, W going to, now I am varying W, same home V W. Now, home, this is, we are fixing the first module V and the other is varying. Now, I do not know whether you have studied this, whether the home is, what kind of a functor it is, right exact, left exact, covariant, contravariant. Where that this, you have done this in your earlier courses. So, I will assume that you know about the home functors. So, home functors. Also we could have also done the tensor functors. So, the tensor products. So, similarly you can think, you can fix one module and vary the other one, right. So, the functors this tensor over A to W or V tensor over A dash, these are the functors from same category to same category. And the good thing about the tensor functors are they are isomorphic because they do not change. So, this is better in that sense. Okay, now with this also you have noted that when do you say a functor is exact? When it carries exact sequences to the exact sequences. So, f is called exact if whenever you have exact sequence v prime v double prime is exact, that should imply f v prime f v double prime is exact. And I am saying this f is from our situation A mod to A mod, category of A modules. Namely, this is f prime, this is f of f prime, this is f of f. So, that is it. Now, we have seen that this home A V W V dash, this is a functor from A modules to A modules. Is it covariant or contravariant? This is covariant, right, because it mapped W to this, and if you have a map from W to W prime, you should have a map from, and what is this map? This map is you take a morphism f from V to W and then compose with this. So, you get in the same direction. So, this is covariant, and you have seen that this may not be exact, this is not an exact functor, but it is which exact? Left exact. So, when do you say a functor is left exact? That means only if you have a short exact sequence, then the exactness will be retained only at the left side, that is, therefore, it is called a left exact. There is more general definition, more general vocabulary there in homological algebra, but we do not need it. So, now the question is, when is it exact? When is this functor exact? So, that will give a condition on V. For some for which what condition on V is there, so that this functor is exact. Similarly, the other one home A dash W, this is now contravariant because it will reverse the arrow. So, this is contravariant. Actually, the study will be similar, no, one will be the dual of the other. So, now I will define an A module. So, definition, an A module P for an A module. So, this definition, okay, for an A module P, the following are equivalent, So, one of them is home A P, this is an exact functor. Two, when we have a diagram like this, V to V double prime to 0, that means the surjective map. So, this is phi, and if you have given a map P to this F, we should be able to lift it. So, given phi surjective and f A module homomorphisms, there exists f bar here from P to V A module homomorphism such that this composition is f bar compose phi is f. If these equivalent conditions are satisfied, then one call the module P to be projective. P is called projective A module. And please check that these two conditions are equivalent. That is not so difficult. You just have to say understand when the sequence is when the functor is exact and this. So, it is similar.